The one that you have seen in the exam, it just have an axial load, and just the footing. There is no moment applied. Now in this case, I'm gonna have here axial load and a moment, and I have the two values for it. And I should be able to develop this pressure distribution. And this pressure distribution, or if you like, call it stress distribution below the footing, is gonna be for the service, right? It's gonna be based on the service load. It's gonna be the service stress. It's gonna be 8 in one side and 2 in one side, 1000 PSF. Now also I need to do it for the factor, because if you like to design here the reinforcement, and the reinforcement is gonna be running in this direction, because it's gonna be cut through the section. So in this case, I need to have it at the ultimate level. Now, if you look here at these two values, it just says service, but you don't know how much is dead load, how much is life load. So in a case like this, and we have here a very good example for it, right? In a case like this, to take it from the service to the ultimate, you just divide here by 1.4, which should be enough, because we don't know exactly how much is dead load, how much is life load. So an average value that makes sense is gonna be 1.4, between 1.2 to 1.6. Now, once you find this stress distribution, you can divide the force here right at this section. This is gonna be the critical section. Now, someone's gonna say, you may have here two sections about the face of the column, which is face of support, right? Now, which one do you think is gonna get you a higher moment value? If you put the forces, it's gonna be this side or this side? You say this side, I'm gonna have force coming this way. Now I need to know the point of application, which is the distance from this face to the point of application of the force. So you have the force value, and then you have this distance. It's going to get you one moment, and then you do the same thing from the other side. You have the force times the distance. Now, which one do you think is going to get you higher moment? It's going to be the right side or the left side?
Right side?
Yeah, absolutely the right side. Look at this, 8 KSF from here, and from here is going to be 2 KSF. This is much higher. So I guess I'm going to be taking only one section, because someone's going to say this reinforcing here, it resists what? It resists 2 moments. One moment is going to be coming from this side, one moment is going to be coming from this side. So I'm going to say, of course, I'm going to be designing for this moment. Forget about this one. I don't really care about this section. Just going to take the one that's going to be controlling my design. I decide here to split this force into two forces, F1 and F2. It is true that I can find out the force for this trapezoidal force. This trapezoidal distribution, I can do just one force. If you want to, I should be able to. You know, this area of this trapezoidal. The only problem is going to be the point of application. How would you find out the point of application or the CG of this trapezoidal? So someone's going to say, yes, it's true. I can do one force like this. You say, this is great, but how about this distance? You cannot find it that easily. Just to make it easier on you, I'm going to find out the force due to this rectangular distribution and due to this triangular distribution. Find out F1 and F2. Then find out X1, which is 1/2 of X, and X2 is going to be 2/3 of this X. And then find out the moment at the face of the column. Once you do this, here's the moment at the face of the column. I have here 1254. Now I can use this to design for the reinforcing. It's going to be a very standard, and you have seen this in more than one design now, that you assume that D minus A over 2 is going to be roughly equals to how much? Can someone help me with this? Ashley?
0.9.
Okay, Ashley, thank you. It's going to be roughly like 90%, right, of the depth. Just a quick estimate, because I need to start at somewhere. Someone's going to say, how can I put the reinforcing? I don't know. Can I put, for example, 15 number 8, or should I put 16 number 7? At the beginning, I don't know exactly how much is this AS needed, because you don't have any idea about this number. And if I tell you this is going to be the rebar size, like this number 8, for example, you say one number 8 is going to be 0.79. You need 11.69. All right. So what you need to do, just take this, divide by 0.79. You get your number of rebars. So it's going to be about 15. So I said, let me put here 15. And here's the total cross-section area that I provide. It's going to be 11.85. slightly higher than this. So I'm just gonna say, how about 14 number 8? Can I try 14 number 8? What do you guys think? If someone says, I'd like to try 14 number 8, should they say, no, this is wrong? Or should they say, yeah, why not? Go ahead and try it. Give it a try.
It depends if it's greater than the area required of the rebar.
But this is gonna be the area required. And someone here put 14. How about if you put 14, Oscar? How many square inches or how many square inches would you get? So I'm gonna put here, just quick assumption here.
I got 11.06, but
So
that's
this
not sufficient.
So what should they do? So they say, no, this is not gonna be a good option. This is
Yes.
bad.
Exactly. We should use 15.
So I'm not gonna go with 14 number 8, right? But
Yes,
someone
you're right.
insists here and say, but I'd like to try it. Is there anything wrong with this? Is this unsafe to
No,
try?
there's nothing wrong.
Because, yeah, I agree with you totally. Nothing is wrong with this because here's what's gonna happen. I just put this in assumption. But maybe if you run the analysis, maybe you're gonna have enough capacity, right? Does it make sense?
Yeah.
Okay, so for example, if you put here 14, it's gonna be almost 11 square inches. So you're gonna find out the actual A, find out the fee man, and then you say here whether it's gonna be covering your demand or not. All right, now Oscar, it looks like it's gonna be your day. So help me out with this.
Okay.
I'm gonna say here, if I use 14 number 8, how much is AS?
Roughly 11.1.
Square inches, right?
Yes.
And in this case, how much is A?
A would be, give me 1 sec.
Sure. Okay, is it 12? Does anyone would like to share, to come with us and volunteer, do some work with me now today, or no?
So I got the A to be
Yes.
1.63.
1.63 inches. Anyone interested to take a few points? Some good points?
I'll go ahead.
Christina?
I'm
Okay.
also interested.
Okay, and also Raman, right? Of course. So I'm gonna say here, it's gonna be for Christina. Can you tell me how much is C?
C would be A, which was 1.63 divided by 0.85, I think.
Yes. Yeah.
Which is 1.92 inches.
Okay. How about C over D ratio?
D in this case is 26.5.
Yeah.
So the ratio is 0.0732.
0.732. How about the
Yeah.
fee factor in this case?
So the fee we assume to be 0.9.
Now, it is not assumed. After you find out C over D, can you tell me how much is the fee factor?
It'd be 0.9.
Excellent. Now, Raman, if you tell me, please, how much is fee man at the end of the day?
What FM?
Fee
FMN?
man, yes.
Let me just.
Yeah, go ahead.
Could you repeat your question to Christina earlier? I wasn't really understanding what you're asking for her when she said 0.9 the first time.
It's right here. Do you see my screen?
Yeah, so I remember she said 0.9 the first time, but then you asked her a question and then she answered it with 0.9 again.
She said, we assumed fee to be 0.9. Here in our analysis at the beginning, we assumed it to be 0.9. But now I'm not asking for an assumption. I'm asking here, based on C over D, what value should we use for fee?
Oh, so we would use C over D on the chart to find?
Yes, exactly.
Okay. Okay, thank you.
Yeah, no problem.
So 1282.9 for
Well,
VMN.
82.
1282.9 for VMN.
Is this good or bad, Oscar?
Sorry.
Now, is this selection for T number 8, is it good or bad for us?
So that would technically pass. It would be okay.
Right. So usually at this stage here, it's just an estimate, right? I want you guys to know this. So in many cases, we go a little bit lower than the estimate or the required here in this analysis, and we should end up with good result. This is what I want you to know, that this is just an assumption, because I have here a couple of assumptions, right? The first one, I say D minus A over 2, let me just take it as 90% of D. The question is, how would you know it's going to be 90% of D? It could be 85% of D, you know, when you look at the analysis at the end. It could be maybe 95%, maybe 98%. So do not decide that this is going to be the final value, and if you're going to be going lower than this, you're going to be in the wrong side. Like in this case, I showed you here a very good case. I just used 14 number 8 with 11.1, which is slightly lower than the 11.69, the needed or the required based on this analysis or this quick estimate. I'm still making it okay, right? I just want to be sure that this match is clear to everyone, right? All right. So today I had Oscar, Raman, and Christina. Okay, thank you.
Professor, how
Yes.
do you, from C over D, like how do you know it's 0.90? Where do you get that from?
It's a very good question. Give me a second. Do you remember this chart?
Oh, okay, yeah, now I know.
Now, how much is C over D according to this? You see this? 0.07. Wow, it's very small. Is giving this side or that side?
The left
Right or left?
or the right.
To the right. So it's gonna be here. So phi of 0.9.
Okay.
Very good. Any questions, Raman? You're good? All right. So I'm gonna say this is gonna be enough, and enough for this slide set. I'm gonna end it at this point. Now I'm gonna be moving to development length for rebars. All right. So I'm gonna say, let me switch to it. Trying to understand what is this slide about. It says development and splice length of reinforcing bars. So I'm trying to understand what does mean by development length, what does mean by splice length. So I have here two items, development and splice length, okay? So I'm gonna put this from the PowerPoint, and later on, I'm gonna give you this few pictures. I'm gonna post them. It's giving a separate file, or maybe just update this file. Look here at the performance of a simply supported concrete beam. Someone's gonna say, is this simply supported? I'm gonna say yes. When I do the analysis, when I do the moment here, I'm gonna say moment M is gonna be equal to W squared divided by 8. I guess everybody's familiar with this equation now, because I was checking with some people and say, well, we don't know what you're talking about. And then later on, they figure out, yes. So I'm gonna say maximum moment, right, is gonna be equal to W times L squared. This is not L2, so I'm gonna say here L squared divided by 8. The whole thing is here is gonna be divided by 8. So what is that for? This is gonna be the maximum moment that you have at the middle of the simply supported beam. This here a simply supported beam, and then attached to two columns. One column is gonna be at each end. Look at the formation. I have here the load is gonna bring this down, and for that I'm gonna see here some tensile cracks, right? Because the maximum moment is gonna be right here in the middle, and once you go here to the support, the moment value is gonna drop down, the positive moment. We call this positive moment because you have the cracks here at the bottom. Once you get close to the support, you're gonna see here's maybe some shear cracks. And look what happened to the column. any connection between a beam to a column, it needs to stay or to remain at 90 degrees as much as possible, because it is usually stronger than the column itself and the beam itself. So look what happened once you start to push on this down. Now this column is going to start to bend outwards like this. In your analysis, you assume that you have here a hinge or a pin, that there is no moment to be transferred from the beam to the column. But reality is there is some moment transfer from the beam to the column, and this is the reason that the column is going to start to bend this way. It's going to start here to push out and push here from here is going to be out. And then all of a sudden, because of this connection, it's going to be actually the rigid connection, which you do not consider at the beginning. All of a sudden, you're going to have your tension on the top, which means negative moment. You know, negative moment, positive moment. Negative moment creates tension on the top, and positive moment creates tension on the bottom. So now all of a sudden you have some moment developed here as a negative moment and some moment developed here at a negative moment, while you still consider it to be simply supported beam. Now this is gonna be trouble, right? Because we were not ready for this. We thought it's gonna be simply supported, meaning only positive moment. Now all of a sudden you're telling us that we're gonna have some negative moment. Now, do we really need to develop this moment here? Do we need to put some reinforcing here to take this moment? You can say no. We're not gonna put something special or something specific. We can just extend the top bars that we're gonna have to the end of the beam to take this negative moment. And someone's gonna say, now what's gonna happen here at this location, right? You have here the bars is gonna be maximum tension. Can I just stop the bar here? Just imagine that you have this rebar embedded in the concrete. Now you start to pull it, right? Now it's gonna come out. So you really need to hook this rebar at the end. How would you do this? You bend the top rebar down, and with that you provide a hook. This hooking the rebar or anchor it to the concrete, we call this development. And this development, you can have it by providing an anchor, or you can have just much longer piece of the beam that sticks out and just extend the rebar. Now let me show you here what we do. Here's the end of the rebar, right? So in this case, we need to bring it down. So the reason that we're gonna bring it down, we are gonna hook it this way. We call this, just you guys know, 9-degree standard hook. So the reason that we do this, to be able to develop the bar. So what does it mean by develop the bar? Develop the bar means, in order for you to gain the strength that you designed for, you need to be sure that the force is really transferred to the concrete. If there is no development for the rebar, once you put this force to the rebar is gonna be coming out of the concrete. Does it make sense? Yes? No? Abigail? Are you here?
Professor,
Yes,
you
Alex.
mentioned that you hook it down. Would you be able
Yes.
to hook the vertical column to go 90 degrees to the left?
Beam left?
Yeah, so for example, that right column that's going up, would you be able to hook instead left?
You wanna hook it where? This side? If you have
Going
another
up is
beam,
what
yes.
he's saying. Or
If you have another beam, you may, but you would like maybe to put it down here within the column itself. It's gonna be much easier for the rebar detailing and for the installation.
Got it. Thank you.
Yeah, no problem. Okay. So this action here we call to develop the rebar. So developing the rebar means that you have a tension force within the rebar, you'd like to transfer it to the concrete. So if you just stop the rebar, like this guy here, see this one, like this top bar, right? This is not developed. This top bar is not developed. This top bar is developed. You see this one is really developed, but this top bar that stops like this, you don't have enough length here to develop it. You either, if you have an extension of this column to the left, if there is another beam in this case, if you just extend it through the beam, now you have development for this rebar. But with the way that we are showing it here, this is not developed. So there's two ways of developing the rebar. Either that you hook it, and we call this 9-degree standard hook, or we do 180-degree standard hook that I'm gonna show you in a minute, right? It's gonna come. And the 180, which means that you bring the bar back, like in this direction, or 9-degree, you just bring it down. There's a length for this hook. So, and the length starts from the face of the column. So I'm gonna say start from this point, all of that, I'm gonna call it here the hook length, which means from the critical section, which is right at face of support, all the way to the end of the hook. There's gonna be straight development, is gonna be from here to the end of the rebar. So in this case, I'm gonna say here the provide development length is less than what is needed by code. In this case, for this top rebar.
Professor, that hook that you just were pointing at,
Yes.
that rebar hook, is it a continuation of the tension rebar, or is it just a different rebar?
Okay. Originally, when you do your design, you don't really design this. Why? Because you assume this gonna be simply supported. You know, at the top of the support, moment is gonna be 0, correct?
Yes, yes.
Yeah. So in your original design, there is no real moment here. So you're not supposed to add any rebars. But you know that because of this connection, you're gonna have some cracks and you need to put some reinforcing bars, right? So what you do here, like in this picture, you can take some of this bottom rebars, bend it, bring it up, and just leave it there. But you don't really, there is no calculations for it.
No, yeah, I see that, but in your picture, I can't tell, like, so that tension rebar, right, that goes horizontal.
Which rebar, the bottom or the top?
The bottom, the bottom.
The bottom, yes.
So that is separate from this hook rebar, correct? That's what I'm trying to.
It is the same. It just
Okay.
happened to be the same. You take the same rebar. Here's the rebar, the red one, right? The thick one. You go, you bend it, you go up, bend it from here, you go up. Then you come to the end of the column, you hook it down.
Okay, perfect. Thank
This
you.
is just to save some material. The reason that they do this is to save some material. Some people
Yeah,
think
that's
that this
what-
is gonna be too much, and
Mhm.
in this case, they can just do it as separate piece of rebar. Look at this. Maybe this picture is gonna be a very good picture for you. Look what happened to the top rebars. Top rebars is coming down, bottom rebars also is going up.
Okay, I see
So
that.
with that, I developed the rebars. Now, where's the developed length for the hook? I'm gonna say it's gonna be start from here. Once it's gonna be going inside the column to the end of the hook. Not to the end of the bar here at the bottom. No, it's gonna be this length, horizontal length.
Mhm.
This hook can be sometimes can be very large, right? It depends on the bar size. So when the bar size is larger, it means that you have more tension force. So now the length is gonna be larger because we need to determine how much is that length, right? It's not that we need to measure it here from the actual construction, but we need to design the needed length. So in some case, I'm gonna say for this hook length, I need 12 inches. You're gonna say, this is good, I provided 16 inch. So I'm gonna say, good job, you're done. You provide enough length. But let's say if the needed is 12 and you provide only 8 inches, I'm gonna say, this is not good. Your bar here is gonna be just coming out. Now what happened here to the force that you have in the rebar? This force is gonna get transferred to the concrete. So you have certain bond between the concrete and between the rebar. So the whole thing here is going to be transferring the force from the rebar to the concrete through the bond between the concrete to the rebar. This is why in lots of cases when the bar is larger, you're going to have more tension force. This is why you need longer length to develop the rebars. Develop again means that you take the force out of the rebar, you give it to the concrete. I'm going to go back here now to this slide set. Now this is going to be the term for this slide number 2. I'm going to be adding all these pictures before it. And look at this. Here's a 9-degree center hook. When you have number 18, you see how big? You see this is going to be a truck. You see this? For a loader. Looks like maybe a crane. Look how big is this, right? I guess if I'm going to be standing, maybe I'm going to be like this here, right? Right? Just imagine how big the hook is going to be for a rebar like this, right? Can get like I'm gonna say, I don't want to say this is gonna be ugly, but can get like very large, which is not good for construction. Okay, now I'm looking here at a detail. Here's a column and here's a beam, and I'm trying to discuss this issue. Not here. Let me put this back. I said here, this rebar, the top rebar, right? Just stops here. But let's say that I have another beam on the left side of this. I'd like now to extend the rebar from here. And same thing, I have another beam from this side. So I'm going to be extending the top bar in the other beam span, if you like. So, okay, here's what you're going to see. Here's a column. And here's a beam is going to be running right and left. Here's one beam to the right, one span, and here's the other span. So now I'm going to be taking the rebars coming from the top, from the left. I need to develop it into the other side, into the other span. To be able to do this, I need to extend it. So I'm gonna say now, where's the development length? I'm gonna say it's gonna be from the face of the column here to the end of the rebar. I'm gonna call this L sub D. D stands for development. Now look at how many rebars do I have. This like plan view, right? Looking from the top, looking this way. How many rebars total? You can say I have 5 rebars. Here's 1, 2, 3, 4, 5. Look at the section. 1, 2, 3, 4, 5. 3 rebars gonna be continuous. One to the side, the middle, and this one. Which means this guy, right? This is gonna be continuous. You can say this also is gonna be continuous. This one's gonna be continuous, right? You can say here, the 2 rebars, I'm gonna stop them at certain point, at LD. Where are these 2 rebars in the plan view? It's gonna be this guy and this guy. I'm gonna call the bars, it's gonna be straight, I'm gonna call them a continuous rebar, I'm gonna call it X rebars, which has these circles, right, or oval shapes. The other 2 rebars, you see this, it says bars Y. Bars Y is gonna be these 2 rebars that I need to stop them. Here it is, bars Y, this guy and this guy. I'm gonna stop. You see, all of them, they happen at the same level, right? But if you like to draw an elevation, it doesn't make any sense if you draw the rebar right here because no one's gonna see exactly where do you wanna stop them. So we just show them to be slightly lower, but in reality, everything is getting the same level. Does it make sense? The reason of that it's drawn this way. So okay. Now development length is gonna be the length from this point to here. For which rebars is gonna be for bars Y or Y bars. The ACI code here gives you an equation. It looks complicated, isn't it? It's a very simple equation. Extremely simple equation. You have just a bunch of factors and you need to go through them, find out these factors from some given tables, and that's it. And with that, you're done. It says here the LD, development length, for deformant bars. What does it mean by deformant bars? Anyone knows? Deformation, the bar deformation. Talked about this at the beginning.
Same as rebars we use.
Just the conventional rebars.
Yeah.
Just, you know, this give you the standard rebars, and they call this deformation. This piece here, this thing, and this thing here, the ribs, they call this deformation. We have another type of bars we call smooth bars, but we don't really use them a lot in concrete. Sometimes we use them, so we have smooth versus deformant bars. Now let me look at this. Yeah, this deformant bars, you look at this, we call this deformation, the thing that sticks out of the rebar. Other smooth bars, yeah, but not very famous, okay? So this gave development length for deformant bars and deformant wires. What does it mean by wires? When you have very thin rebars, in certain applications we have them, so this equation works for both of them. For me, I care about deformant bars and that's it. It says here the development length equals 3 divided by 4. I'm gonna say this is good, this is gonna be constant. I shouldn't care about this, just numbers given to me, constants. F sub y, I understand F sub y is gonna be yield strength. Now my question to you, should you use this in psi or ksi in this equation?
PSI,
Psi, why is that?
ACI code.
The whole code is based on psi. So only chance that you're going to be using ksi if you have f sub y divided by f prime c, for example. But once it's here square root of f prime c, you got to be careful because everything here is going to be in what? In psi. And then it's say divided by square root of f prime c, and then you have here this lambda. Do you remember this lambda for lightweight concrete or no?
Yes, 0.75 and 1, I think.
Exactly. Okay, very good. So it's going to be the lambda for the lightweight concrete. Most likely work with normal weight concrete, and this lambda is going to be equal to 1. So I'm going to say this part of the equation, right, is simple. So what is that? What does it mean by dB?
Diameter of the rebars.
Good. So when the bar is going to get larger, I need more length, which makes sense, right? When the yield strength is going to get larger, it means that I'm going to have more force to transfer to the concrete or to develop. It means the length is going to be larger. When you have a stronger concrete, it means that the bond between the concrete and the reinforcing bar is going to be larger. right? It's gonna be higher, and therefore the length is gonna be smaller. Make sense or no?
Yeah, that makes sense.
Okay. So let me put this here. I'm gonna see here L sub D. What happened to it? It's okay. Let me do this. Let me put this to be kind of light background so you can see the red. LD is gonna be going up or down when f sub y. So let me start by saying, okay, when DB is gonna be going up, what happened to LD?
Goes up.
LD goes up or down?
It increases.
Goes
Goes
up.
up, yeah, increases. When f sub y goes up, what happened to LD?
It goes up.
Yeah, based on this equation, I guess. I mean, if you cannot, let's say, if you have been asked the question like this, like one of these conceptual questions, you should be able to answer by just looking at the equation, right? So what happened when F prime C goes up? When you have a stronger concrete, it means higher bond. So what happened? LD goes
LD
lower.
goes down. Oh,
Okay, so I'm gonna say LD goes down. There is no on down, right? When you abbreviate it, there is no. Usually we say like this, DN, just DN. It goes down. Someone's gonna say D sub N. You know what? Yeah. I said, okay, everything here is good. I understand this. I know this. I know this. I know this gonna be for the lightweight. So when you use lightweight concrete, what's gonna happen to the development length? Well, lambda is gonna be, let's say, 0.75. So what's gonna happen in this case? The length is gonna
Goes
be
up.
longer. Why? Because the concrete is not as strong as a normal weight concrete. Yeah, it makes sense for the way that they develop this equation. Just say I have some factor in this called psi. Psi T, Psi E, Psi S. I don't know why they use this term or this symbol. Someone else can have been calling it maybe KT, KE, KS, or maybe K1, K2, and K3, you know? So don't be scared when you're looking at the symbols here and say, what is that, right? But we have some factors. The first factor here is called sub T. Another factor is psi sub E for epoxy. Psi sub S is gonna be for the size. So the first one is gonna be for top rebars versus bottom rebars within the beam. Second one is gonna be about epoxy coated rebars. You know, sometimes for the corrosion protection, they paint the rebar itself with some epoxy, you know. And this one is gonna be based on the size. So, okay, we're gonna be going through all of these factors. Also, it says there's a factor called C sub B. It's actually about the concrete cover. So C here, you know, usually we use C, it stands for cover. KTR, we're gonna be going through this, divided by DB. And it says here, the maximum value for this is how much? Let's say that you run the analysis, you're getting 5 or 3 of this. You just take it 2.5. If it's gonna be less than 2.5, good, take the value as is. Once it's gonna be getting higher than 2.5, you just limit it to 2.5 in this equation. All right? Now I'm trying to understand all of these factors here. This is gonna be the new items that I need to learn about. And you know what? The code is so simple. It says epsilon T for the top rebar. It says when you have horizontal top reinforcement and you have a depth more than 12 inches of concrete, take a psi top of 1.3. All other reinforcement is gonna be 1. So I'm gonna come back and say, how about for columns? How much of psi sub T should I use? The vertical rebars is gonna be 1.3 or 1. Alexis. Oscar, go ahead, answer.
No, I was just gonna ask you, can you repeat that question again?
For columns, when you have vertical rebars, which psi sub T should I use?
I think 1.
It's gonna be 1, absolutely, because it says here horizontal top reinforcement, and this one says here all other reinforcement. And what is the definition of top reinforcement with the code? Can someone read here between the lines and tell me the answer for this?
As long as it's above 12 inches of the concrete.
Exactly. So it means if the entire beam section is only 10 inches, would you consider to be top reinforcing or bottom reinforcement?
Bottom.
Bottom. So it is true that you may look at the beam, right? Here's a beam. And then maybe you see a couple of rebars here. Here's one rebar. Here's another rebar. But because the total depth of the beam is, let's say, 10 inches, I'm going to consider both of these two rebars to be bottom rebars only for this analysis. It is not when I'm doing here the flexure analysis or moment capacity, but only for this case, I'm going to say psi sub t is going to be equal to 1 for both of them because the depth of concrete below this rebar is going to be maybe about 7 or 8 inches, less than 12 inches.
So
Very
if
good.
that section was expanded vertically and there was a third point, right?
As long as the
mhm.
distance from here, let me put it here. If this distance from here to there, right, is going to be less than 12 inches, psi sub t is going to be equal to 1.
Got it.
All right. How about this epoxy coated? It's going to be simple. The problem is going to say, is it epoxy coated or no epoxy? It's going to be epoxy coated. It's going to be what? And you have certain cover. You see the cover is going to be smaller than 3 dB, 3 times the bar diameter. And the clear spacing is going to be smaller than 6 dB, which means 6 times the bar diameter. Your psi sub E is going to be 1.5. Right? All other conditions of epoxy coated bars is give you 1.2. If no epoxy bars, like the regular bars, take it to 1. And they give me here a note. They say, after you find out your values here, right? After you find out psi sub t and psi sub e, what do you need to do? I'm going to go back here one slide. You need to multiply psi e times psi t times psi s. It says here, just the product of this psi t and psi e should be less than 1.7. So let's say my analysis determined to be equal to 2. What should I do? Forget about the 2 value and just use 1.7. Okay? How about the psi s? Yes.
Sorry, could you go back? So if it's greater than, we just use 1.7.
Just use 1.7.
Okay.
It says here, look at this. If psi sub t, psi sub e, the product is going to be less than or equal to 1.7. So great. I did the multiplication. It is 1.5. Good. Use 1.5. I did it 1.6. Great. I did this multiplication turns to be 1.8. What value should I use?
1.7. Okay,
1.7
thank you.
because it says it's going to be less than or equal. Same thing like here. You do the analysis for CB plus KTR divided by DB. Now it turns to be 3. What value do you use for this term? Denominator. It's going to be 2.5. This kind of repeated this question, or not this question, this kind of concept of having a cap or a limit in the ACI code, you're going to see it more than once. So be used to it. What is psi s? It's going to be about the rebar size. It says it's going to be equal to 0.8 for number 6 and smaller, 1 for number 7 and larger. And lambda is going to be the lightweight concrete aggregate. It's going to be 0.75. So I think here, this term is going to be simple. It's going to be 3 factors. You just need to know the data. They have epoxy coated, the section, dimensions, so you can figure out is going to be top rebars or other rebars, bottom or vertical, and then the size of the rebar. And here's the size of the rebar. So the only thing here left for us is going to be CB plus KTR divided by CB. If you are able to understand this, we're done with this. You can say scary equation. Looks tough, but it's so simple. Okay. What is KTR? It says KTR, this to take the effect of the transfer reinforcement, like the ties. You know, when you have ties, and then they give an equation. For me, just take it to 0. So forget about this equation. Just give it to you here, right? And the slide said, but I'm not going to be using it. So forget about this equation. Let me put here cross. Just take KTR is going to be equal to 0. So this KTR is going to be equal to 0. I don't need it. Let's say here, put it equal to 0. You make it simple for me. So, okay. Put it here so it's going to stand out. So, great. So I need to understand what is this C sub B. Now, I guess you guys are familiar now with everything that you have in this equation. F sub Y yield strength, lambda 0.75 when you have lightweight concrete. F prime C, the strength, you know the strength, concrete strength. If psi sub T is going to be for the top reinforcing versus bottom reinforcing for vertical. E, epoxy coated. S, the rebar size. And the last thing is going to be C sub B because D sub B is going to be the rebar size. C sub B, what's C sub B? It's going to be the only thing left to be able to do an example on this. Just say, let's look here at this picture. I'm just going to be skipping some items here. Just go through this example, just show what does mean by C sub B. Here's the rebars that you're trying to develop, right? It's going to be these two rebars. Here's the tie. You can say the CB is going to be the distance from the center of the rebar to the top of the concrete. So, okay, that's it. Now I'm going to say also, if you are developing this rebar, it's going to be the distance from here to there or the distance from here to there. So I need to use to you more than one check. So which one do you think is going to be controlled, the smaller or the larger of the CB? So I'm going to say I may have more than one CB for this rebar. Here's one CB, from here to there, here's another CB. I'd like to take the smaller of the two, right? From the center of the rebar to the edge of the concrete. When you have lots of concrete cover, it means that you have good media here to transfer the force from the rebar to the surrounding concrete. When this here becomes very thin, you're gonna have a hard time to make this development happens. And in this case, you need to have longer development length. So actually, if you like to embed in a rebar in the concrete, you'd like to have lots of concrete to surround it. And also, if you have two rebars at the same time that you're putting tension on, like here, this rebar and this rebar, and you're trying to develop this rebar here, you're gonna have here two concerns, or two items that you need to be concerned about. Number one is gonna be the amount of concrete, right, surrounding this rebar from this side to the top, and also the other CB distance. You're gonna be splitting these two zones for each rebar. You're gonna say, here's the first rebar, is gonna be taking this size here, or this location, or this concrete volume to develop the bars through it, and this gonna be the other concrete volume that you're gonna be putting the rebar through.
So it's like tributary area, but for-
Exactly, very similar to it. You say how much confinement that you have or amount of concrete surrounding this rebar. So in this case, you're gonna say, I have here for this rebar, I have CB1 and CB2. Now, which one to pick? If I give you some dimension, I'm gonna say, pick the smaller. So in this picture here, this says here 2 inch, right? And then you have the tie size, and then you have 1/2 inch for the rebar size, because it says here number 8, versus it says here 3 inch clear. So in this case, the distance is gonna be how much? 1.5 inch plus 1/2 inch for this is gonna be 2 inches. Does it make sense? I'm trying to figure out here CB2. How much is this CB2? This rebar size from this point to that point is gonna be equal to 1 inch. Why? Because it's gonna be number 8.
Professor, so the 3 inches is the red lines,
Clear.
right?
Yeah, you see
oh,
this
okay.
red? No. It is, look at this. 3 inch clear from this line to this line, from the face of the
Mhm.
to the face. So in this case, CB2
Oh,
equals,
okay, right.
yeah, CB2 is gonna be how much? You can say it's gonna be equal to 2 inches. Yes
Got
or
it.
no? Yeah, it
Yes.
makes sense. Why? Because from this point to that point, I'm gonna say from here to there, right, is gonna be 1.5 inch. It's gonna be 1/2 of this. You had 1/2 inch for one radius of this rebar. So it's gonna be 2 inches from this solid line to this dash line, and this what you call here CB number 2. How about CB1? CB1 is equal to the following. I'm gonna say 2 inches plus 1/2 inch for the tie, because it says here number 4, right? So it's gonna be 2.5. Another 1/2 inch for the radius of the rebar. It's gonna be 3 inches. So based on this analysis, C sub B1 is gonna be 3 inches, and here C sub B2 is gonna be equal to 2 inches, right? And my question is, which one do you think is controlling your analysis for development length? Yes, I'm gonna pick here
CB2.
the smaller of the two. It's gonna be the 2 inches. And here's the analysis for it. Look at this. CB is going to be 2, which is just 2 clear, plus 1/2 for the tie, plus 1/2 for the rebar size is going to be 3 inches. Okay. And CB2 is going to be 1/2 inch or half of the total distance. Total distance is going to be 3 inch plus 2 times 0.5 from each side. You divide the whole thing here by 2, it's going to be 2 inches. Like in here, 2 inches and 3 inches. And which one's going to control it? Is going to be the 2 inch. Now let me go back here because that was just through an example. Let me go back here to my equation and see if this makes sense, which one to pick. Let's say this CB is going in here, right? Look at the location of this C sub B factor within the equation. When C sub B goes up, what's going to happen? You say development is going to be smaller. And in this case, you're going to have lots of concrete to surround the rebar. But when you have a very small cover and the rebars are closely spaced, what's going to happen for CB? It's going to be smaller and development length is going to be larger.
Could you repeat that one more time, that second
Yes.
part?
This CB, right? Which means the distance to the cover. When it goes up, what does it mean by goes up? Goes up means that you have more concrete to surround the rebar.
Mm-hmm.
Now you'll need less development length. Make sense? When CB gets smaller, it means that you're going to have less concrete to surround the rebar. What's going to happen? You need to have longer development length. Yes?
Mm-hmm.
Okay.
Thank you.
Excellent. Very good. Okay. Very good. Excellent. I'm happy with this. Now, let's look here. We said KTR is going to be equal to 0, right? Let's give it the simple way. Just take it equal to 0. Now, also, for this case of D, I'm going to say, what is case of D? I'm going to say, you know what? Where is case of D? Do you guys see here case of D? Just wondering, where is case of D? Do you see it? Yes? No?
No.
No? Okay. I'm going to say, all of a sudden, they say there's a factor called case of D. And what is case of D according to the code is going to be equal to 3 divided by 40 Fy divided by square root of A prime C. So I'm going to say, this is actually going to be case of D. We call this case of D. Let me put it here. This is going to be K sub D here. So K sub D is going to be equal to this factor. So either that you do it by hand, if I give you here F sub Y, you have the lambda value, you have F prime C, or you can just look it up in this table. I mean, it doesn't make any difference because you can just take F sub Y and F prime C and just use this equation or just use it from the table. I myself, I don't really look at the table. I usually use this equation. It doesn't take that much time, you know, it's going to be taking maybe 20 more seconds or half a minute to do it. So, okay, good. Now I have all the terms needed, but one more item here that we'll discuss it later when we have an example. But for now, we're just going to skip this. Okay? The procedure, the steps, if you like, go here in steps. Number 1, find out KD. What's KD? Do this, right?
Mm-hmm.
Or do it by hand, use the equation. Now, figure out or determine the values, absolutely for the top, epoxy, size, and lambda factor. Check this product.
Those values would be given on like a problem or no?
I'm not going to say psi T or psi E or psi S is give you like this, but I'll give you some description. I'm going to say epoxy coated, so you know what I'm talking about.
Mm-hmm.
If I didn't mention epoxy coated, it means it is not
It would-
epoxy coated, so you just take it to 1.
One.
So these values, you'll figure it out yourself based on description of the problem, but the value is not going to be given to you. Now you need to check this product, psi T and psi E. It is on 1.7, more than 1.7, you take it 1.7, and then you do the C sub B. How's that? You look at the geometry of the problem, and then you see the edge distance, or the spacing, or you see the cover thickness. And then you do KTR. How much is KTR? You said?
0.
0. Yeah, just take it 0. Forget about the one less item to care of. Now you need to check CB divided by DB. If it's going to be more than 2.5, just take it 2.5. So we know the check, right? This one, I'm going to ignore it for now to get to an example. And then I'm going to say now you should be able to figure out L sub D. Your minimum value for L sub D is going to be 12 inches. This is gonna be a nice problem in your final. You cannot miss it. And you don't have any challenge in this problem here. It should be straightforward, very simple. Just a bunch of factors and use this equation. And the good thing, you have one example, and then you have another example, and then you have a third example in the other slide set, the upcoming one. Any questions before we finish for today?
No, no questions.
All right, you're doing very well, Oscar, today. What's happening? What's going on?
Huh?
What's going on?
Oh, nothing. Just paying attention.
Okay. All right, good luck, Oscar. All right, wish you the best. All right, you guys have a good night. Go please ahead and sign out.
Thank you, Professor.
All right, good night.
Thank you, Professor.
Thank you. Good night, guys.
Professor, out of curiosity, will you be posting up the next submittal in the next few days, or?
Yes, it's
Okay.
gonna be tonight or tomorrow morning.
And
Yes.
I assume that it'll be on this topic?
Yes, it's gonna be in this topic because we have done the foundation already.
Okay. All right. Thank you.
And just, you know, you should be able to finish it by just reading the example and follow what's in there. So if you want to finish it. I mean, over this weekend before we are done with the lecture covering the example, you know.
Okay. And then you're talking about the examples that are in today's.
Yes, I'll cover it next time. But what I'm saying is the example is so simple, so you can just read it yourself and do it if you want to, and be ready, so you can invest your time instead of waiting, you know.
Yeah. Okay. Thank you. Have a good night.
Right, no problem. Right.